In section 7.3, we're going to be applying that central limit theorem, and we're going to be focusing on trying to make sure that we remember which type of situation are we dealing with. Are we dealing with the sample means, or are we dealing with the sample proportions as we apply that central limit theorem? So that's going to be the key thing for this lesson, just differentiating between the two and making sure we're using the correct formulas for those. So our sampling distribution, suppose that x is a random variable with a distribution that may be known or unknown. It can be any distribution. When we talk about the sample means, the shape of the sampling distribution, x bar, is approximately normal if n is greater than or equal to 30. Mu sub x bar is equal to the mean of x. The population mean is the same as the sample mean. The standard deviation of x bar will be equal to the standard deviation of the population x divided by the square root of n. And remember, the square root of n is our sample size, so this is called the standard error of the mean for a sample size of n. When we talk about sample proportions, the shape of the sampling distribution of p hat is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. The mean of the sampling distribution of p hat is mu of p hat equals p. In other words, it's the same as the proportion of the population. The standard deviation of the sampling distribution of p hat is going to be sigma sub p hat, and remember that is going to be the square root of p times 1 minus p divided by n. Recall, given a sample size n and the probability of success p, when n times p times 1 minus p is less than 10, we can use the binomial distribution to calculate any of those probabilities. So if we don't have a large enough sample size, we can go back and we can use binomial probabilities. Example 7.8, the city of Raleigh has 9,800 registered voters. There are 2 candidates for city council in an upcoming election, Brown and Feliz. The day before the election, a telephone poll of 250 randomly selected registered voters was conducted, and 142 said that they would vote for Brown, 90 said that they would vote for Feliz, and 18 were undecided. Give the sample statistic p hat for the proportion of voters surveyed who said that they would vote for Brown. And then the sample statistic p hat suggests that we might expect how many of the 9,800 registered voters to vote for Brown. So we're going to go ahead and do that. Here's our information. To find p hat, remember we take the number of individuals who have that certain characteristic. And in this case, our characteristic is they said they would vote for Brown. And that was 142 out of the total number sampled, which was 250. So we'll just go ahead and divide that. 142 divided by 250. And that gives us 0.568. So that's the first part of our question, to find p hat. The second part is to identify what does that p hat suggest that we could expect from those 9,800 registered voters. How many of them would we expect to vote for Brown? Well, if our proportion carries over the 0.568, all we would have to do is take 0.568 times 9,800, and that would be our number of voters who would vote for Brown. That's our suggestion. So when we multiply that, we're going to get 5,566.4. Obviously, you're not going to have 0.4 of a voter, so 5,566 would be the number of voters that we would expect to vote for Brown in the election. Example 7.9, in an effort to cut costs and improve profits, many U.S. companies have been turning to outsourcing. In fact, according to Purchasing Magazine, 54% of companies surveyed outsourced some part of their manufacturing process in the past 2 or 3 years. Suppose purchasing contacted 555 of these companies. What is the probability that 338 or more companies outsource some part of their manufacturing process in the past 2 or 3 years. Write your answer as a percentage rounded to 2 decimal places. So now let's do the math and calculate this. P in this case is 0.54. That was from the magazine information. That's right here, 54%. We turn it into a decimal. And that is, if you remember, that is our, let me rewrite that. That's going to be our mean of P hat. Okay, the next thing is the standard deviation of P hat, and that is going to be the square root of n, 0.54, times 1 minus n, so 1 minus 0.54, divided by n, which is, oh, those are the p's, sorry, I think I said n's. And the n value is 555. So p times 1 minus p divided by n, we're taking the square of that. So just typing that into our calculator, we're going to have 0.54, whoops, the square root of 0.54 times, parentheses, 1 minus 0.54 divided by 555. Close our parentheses there. And we get approximately 0.0212 if we round that off to 4 decimal places. All right. So when we're looking at this now, we're going to be able to set this up with our calculators. But the one other thing that we have to do is we have to think about the fact that they are giving us a raw data value and we need it to be a proportion. So the question says, what is the probability that 338 or more companies outsourced? Well, we have to figure out 338 is what part of the total that they surveyed, 555. So let's divide that, 338 divided by 555, and we get 0.609. Okay, so now when we set up our problem is going to be, what is the probability that P hat is greater than this 0.609. And again, we're going to use these other values to help us, and we're going to pull up our calculators for that. So now that we've got our values back here where we want them, we want greater than 0.609. So our lower boundary is going to be 0.609. Our upper boundary, that's going to be the 1E99, because we're just saying greater than this. Our mu value, remember that was the 0.54, so we're going to put that in. And then our standard deviation is this 0.0212. And we'll paste that in and hit enter. And we get this now right here again. We've got to be careful with this E -4. You can't have a probability that's 5.6. So you know that something's wrong there. But what we get here is 5.68, we'll say. That means times 10 to the -4th. So that means we take this decimal point and we move it over 4 spaces. 1, 2, 3, 4, and we fill in with zeros. So if we want this to the nearest percentage with 2 decimal places, oh, okay, well so what we've got here is 0.0006 if we round that off, and if we change that to a percentage, remember we move the decimal point back 2 spaces, that would be confusing, but it's 0.06% chance. So a very low chance that they have that many people who, or that many companies who have outsourced some part of their manufacturing in the past 2 or 3 years, because that's over 60% and the average is 54%. So moving on to part B. What is the probability that 285 or more companies outsource some part of their manufacturing? So again, we've got to take that 285 and divide by 555. And that means the P hat that we're dealing with here is 0.514, we'll say. So we're trying to find the probability that P hat, what is the probability that 285 or more, so is greater than or equal to 0.514. and I had to erase it, but remember that our mu sub p hat is 0.54, and our standard deviation was the 0.609. So we'll go over here to our calculator again, second variables, down to normal CDF. And this time our lower boundary is the 0.514. Our upper boundary is still the 1E99. And all these other, oh, actually, yeah, the 0.609 was that other thing. So it's a good thing this is still on here for us since I had to erase it. 0.0212, that was our standard deviation. So then we'll go ahead and paste this and hit enter. And we find out that our probability of it being more than 285 is going to be 0.88. Let's see, that 99 will get rounded. So 8900 if we round that off. So that'd be 89.00% if we change that over to a percentage. This one doesn't actually say to change it to a percentage, so maybe it doesn't matter, but they did on the last one. Then for part C, it says, what is the probability that 48% or less of these companies outsource some part of their manufacturing? Well, this time it's actually easier because we don't have to find the p hat value. They're just telling us we want p hat is going to be less than or equal to the 0.48. So when we go to our calculators again, we're going to go second variables. We're going to go down to number 2, normal CDF. This time our lower boundary is the negative 1E99. Our upper boundary is the 0.48. And then these other two values just remain as they are, the 0.54 and the 0.0212. And we're going to go paste and enter. And so notice here we get a pretty small number. It's going to be 0.0023 or 0.23% if they were asking for a percent. Remember, to convert from this decimal number into a percent, all we do is we take that decimal point and move it over 2 spaces. And that's how we convert from a decimal to a percent. For example 710, it says engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean of 6.7 inches and a standard deviation of 1.6 inches. Suppose we select random samples of size 41 from the population. What is the probability that the breadths of male heads average is more than 7.3 inches? So let's give ourselves some space to work here. Suppose we select random samples. Now notice this one, we are dealing with a sample mean here. So this is going to be a little different than the last one when we were dealing with the proportions. So part A, suppose we select random samples of size 41. So n is 41. And what is the probability that the breadths of male heads average is more than 7.3 inches? So we're looking for the probability that x bar is greater than 7.3. Now, we already know that mu sub x bar is equal to 6.7 because that is the same as the mean of the population. But our standard deviation of x bar is going to be equal to the original standard deviation, 1.2 inches, divided by the square root of n, which is 41. And just to remind ourselves, we need to have a sample size greater than 30 for these sample means so that we can be assured that this is a normal distribution. So let's go ahead and type this in. We're going to have 1.2 divided by the square root of 41. And that's going to give us about 0.1874. We'll go with 4 decimal places there. All right, we may not need that many, but that gives us enough accuracy. And then we're just going to type this into the calculator again. So second variables down to normal CDF. We want greater than, so our lower boundary is going to be that 7.3. The upper boundary is going to be the 1E99. We know that the mu, the mean, is 6.7. And we know that our standard deviation is 0.1874. 4. So we're going to find that probability. And what do we get there? Not a very good chance. We've got 0. Okay, so let me write it out here first and then we'll convert it. So it's 6.83 times 10. And again, remember, you can't have a probability bigger than 1. So if you see 6.83, it tells you there's something going on here. Times 10 to the negative 4th. That means we move the decimal point over 4 spaces. That's going to give us 0.000683. So if we round that off to 4 decimal places, which is what we usually do, it'll be 0.0007 for our probability that the sample mean is greater than 7.3. For part B, in what range would we expect to find the middle 36% of most head breadths? This is one you definitely want to draw a picture for. So here's our middle. We know that's the 6.7. And we just want a little bit on each side so that this total amount here is going to be 36% of the middle 36% of most head breadths. So this is going to be one of those inverse problems. So if we've got that middle 36%, that means 18% is going to be here and 18% is going to be here, or 0.18. We also know that this side is 50%, or 0.5. So since our calculator always finds area to the right, if we want to find this area from here this way, we're going to take this 0.5 and subtract the 0.18. So 0.5 minus 0.18 is going to be 0.32. That's going to be the first number we're going to find. The second one is easier because we're just going to add these two numbers together, the 0.5 plus the 0.18, so that's going to be 0.68. So let's find these two boundaries, and here we go. So second variables, we're going to go down to number 3, inverse normal. And the area for the first one is going to be 0.32. Mean value is 6.7. And we know that our standard deviation is the 0.1874. And paste and hit enter. And so we know our lower boundary here is, let's see, they're giving it as 1 decimal. We're going to go 2, so 6.61 inches. And then the upper boundary, we're going to do the same thing. Second variables down to inverse normal. But this time our area is 0.68. Everything else stays the same. Paste that, hit enter. Our upper boundary is 6.79 if we round that off to 2 decimal places. And again, remember our rounding rules. Since their original values were given to us at the nearest tenth, we'll keep 1 additional decimal place. So we would say the middle 36% of head breadths there is between 6.61 inches and 6.79 inches. For part C, if we were to draw samples of size 57 from this population, in what range would you expect to find the middle 36% of most averages for the breadths of male heads in the sample? So the question here becomes, what happens when we change the sample size from 41, which is what it used to be, to 57? So we have to change our standard deviation then. So 1.2 would now be divided by the square root of 57. And so that is going to be 1.2 divided by the square root of 57. And that is 0.1589. And so that's what's going to change. Our picture is actually the same. The only difference is that we're going to have a different standard deviation now. So we're still going to have, just going back to your previous picture, the 0.32 for this part and the 0.68 for this part. So second variables down to inverse normal. In fact, I'm going to just do this one first. So 0.68 we've already got, 6.7 we've already got, but our standard deviation is now 0.1589. Paste it, hit enter. So the upper boundary this time is 6.77. I don't want to put a dash there for now. And then to do our lower boundary, second variables, inverse normal. And we're going to go 0.32, and the rest hasn't changed. So go ahead and hit enter, and we get 6.63. So notice if you take a larger sample size, it compresses everything towards the middle even more. So our range where that middle 36% is expected to be is going to be even smaller than it was when we had sample sizes of 41. That is the end of section 7.3. So you can go ahead and work on those 6 problems. I think it's 6 problems. And then remember, again, the key difference is, and I tried to point that out, I probably didn't do it every time, but sometimes you're dealing with sample proportions, and then you have your formula for coming up with your standard deviation, and you need to make sure that you're using that. Well, let's just summarize. Mu for sample proportions, mu sub p hat is equal to p. For the standard deviation of p hat, remember that is the square root of p times 1 minus p divided by n. So those are your 2 values you need for that one. When you're talking about sample means, the mean of the sample means is just the mean of the whole population. And then the standard deviation of the sample means is that original standard deviation divided by the square root of n. So the sample size affects both of those, but you've got different formulas, so you've got to make sure you're keeping track. Are you dealing with a proportion? Or are you dealing with a sample mean? So keep track of those, and that will help you with this assignment.